here is that there are three different tests that are being displayed when you fit a logistic regression model to that 2 by 2 table. And notice all three of these tests are very similar in their values. And you can use any one of those three as your concluding test or your basis for telling you whether there's a statistically significant association between sex and your risk of getting heart disease. For the 2 by 2 table, you'd probably use the middle test, the score test. That's the same as that observed minus expected comparison for the observed 2 by 2 table with the expected 2 by 2 table that we looked at 2 weeks ago. But notice we have this other test which is essentially the same, this likelihood ratio test. That's based on comparing the fit of two models, the model that does not contain sex and the model that does contain sex. And what we're asking is, do we get an improved fit using this minus 2 log L as a measure of fit? And that's why the likelihood function is very important. It's not only just telling us what the odds ratio will be by looking at the coefficient V1 of sex and taking e to that number, but also by looking at the values for the likelihood, we get another way of doing tests of significance. So in this case, the logistic regression model is giving you three different tests for testing the null hypothesis that the coefficient of sex is equal to 0. If the coefficient of sex is equal to 0, that means the model becomes log odds of getting disease is equal to B0 for everybody. It doesn't matter whether you're a male or a female. If B1 is equal to 0, we're back to the model that just has the intercept in it. That was the intercept-only model. Well, there are these three different tests, as I mentioned. I was just describing the likelihood ratio test. The score test is the one we get from the 2 by 2 table if we do the usual chi-square test of association. The third test is what is known as a wall test, named after the statistician Wall. And basically, it's of this form. Let's look at, well, let me review them first. I'll get to the wall test in a minute. This is what the likelihood ratio test does. It compares two models. The model that says your log odds of disease is equal to B0 plus B1 times your value for sex, male, 1 if you're a male, 0 if you're a female, compares that to a model which only has the intercept in it. It says everyone's log odds of disease is equal to one number, just the intercept value, say C0, regardless whether you're a male or a female. What the likelihood ratio test is doing is comparing the fit of these two models and asking if you get a better fit by adding sex to the model. If you didn't, then what that means is the model with sex is essentially the same as the model without sex. The model without sex is the null model, the model that says sex has no influence. So this is the way we test the significance of a risk factor, sex, by taking the value of minus 2 log L from the model without the covariate, without sex, and subtracting from it the value from minus 2 log L from the model with sex in it. The wall test does it a different way. What it does is look at the coefficient of sex and asks, is that a significant coefficient? It compares it to the number 0. Essentially, if I took B1 and subtracted 0 from it, I'd just have the number B1 back again. So what the wall test is doing is comparing the observed log odds ratio to what you would expect the null hypothesis is true. If the null hypothesis is true, we would expect the odds ratio to be 1. The log of 1 is equal to 0. So if the null hypothesis is true, we would expect the B1 value to equal 0. What the wall test does is compare the observed value for B1 to the expected null value of 0. Ask, is it different from 0? In terms of standard error units, we'll talk about standard error at the end of this morning. Remember, what the standard error is, it's a measure of precision. It says if you did many studies like the one you just did, each time you fit a logistic regression model to your data from that study, each time you get a number for B1, the number for the log odds ratio from that model for that particular data set. Standard error of B1 is the standard deviation of all those numbers. So it's asking how many standard deviation units is the observed number B1 from your one data set, when you fit your model to that one data set, from the value of 0. So if we go back to the model itself, Here's the value for B1 in that model, 0.707. The standard error, the estimate for the standard deviation from your data set is 0.13. So let's divide the 0.707 by the standard error, 0.139. If you divide 0.7 by 0.1.3, you get a number around 5. If you square that number, that's what's listed here, the 25.75, that's the square of the quotient, B1 divided by the standard error of B1. This is the wall chi-square test. So what the wall chi-square test is doing, taking the value for B1 divided by its standard error and squaring it. If the null hypothesis is true, that number should look like a typical value from the chi-square table. So what it does is it looks that value up in a table. And let me go back to the model once again. So it takes this number, the coefficient 0.707, divides by the standard error, squares that quotient, and it says, if the null hypothesis is true, this should look like a typical value from a chi-squared table with 1 degree of freedom. Why it's 1 degree of freedom is essentially we're only looking at one risk factor, male, in this model. Another reason it's 1 degree of freedom is that when we did the likelihood ratio test, we compared a model with the intercept only, C0, to a model with the intercept plus a coefficient of sex, a B0 plus a B1. So there are two coefficients being estimated in the model we fit. It would only be one coefficient being estimated at the intercept. It's the only factor in the model. That's why all these tests have 1 degree of freedom. Notice they're all very similar to one another, so you have the liberty, the choice, of using any of these three different tests of significance for trying to test the null hypothesis. Null hypothesis, it says sex has no influence whatsoever on your risk of getting heart disease. No matter what test you get the same similar p-values because the test statistics are very similar. So when you have a 2x2 table, SAS gives you three different tests for testing the association of that risk factor with that outcome. Okay? So let's move on. The other thing we did on last week is we looked at other tables that had more than 2 rows in it. Remember, we looked at the relationship between smoking, broken into 4 categories: packs, a non-smoker, packs equals 0, a 1-pack smoker, packs equals 1, a 2-pack smoker, packs equals 2, a 3-pack smoker, packs equals 3. We looked at a 4x2 table. And then we looked at a model that essentially reproduced that 4x2 table, a model that represented smoking by 3 indicator variables. Packs 1, remember, was a 1 if you're a 1-pack-a-day smoker. It was 0 otherwise. Packs 2 was a 2-pack-a-day smoker. Was a 1 for a 2-pack-a-day smoker, 0 otherwise. And Packs 3 was a 1 for a 3-pack-a-day smoker, 0 otherwise. We fit this model last week. We got the following printout. And here's the value again from -2 log L from the model which only would have the intercept, saying everyone has the same risk of getting disease regardless of their smoking level. Here's the value for the model with the intercept and 3 indicator variables to represent the 4 different categories of smoking. The -2 log L has dropped from 1350 down to 1342. That's a drop of 8 points. It would be the basis of the likelihood ratio test. Last week, when we looked at the corresponding 4x2 table and just looked at the chi-squared test for that 4x2, not the 8.1 we have from the likelihood ratio test. Last week, we saw a value of 8.77, but very similar. And likewise, there's a wall test. All these are testing the same null hypothesis. This is the global null hypothesis. The global null hypothesis means that all the risk factors in the model have coefficients equal to 0. Well, in this particular model, we only have one risk factor, smoking. But remember, the way we represented smoking, if I go back to the model, is we represent it by having 3 risk factors here, 3 variables, packs 1, packs 2, and packs 3. So now, the global null hypothesis is testing that the coefficient of B1 and the coefficient B2 and the coefficient B3 are all equal to 0, that none of these factors, packs 1, packs 2, or packs 3, are important. So now we're testing a global null hypothesis